today we are talking about geometric series, again related to geometric sequences. So last time we talked about the difference between a sequence and a series. So just to remind you, a sequence is just an ordered list of numbers, and a series is the sum of an indicated amount of terms in a sequence. So for example, 1, 4, 16, 64 is a sequence. 1 plus 4 plus 16 plus 64 and so on is a series. So another reminder about the difference between a finite series and an infinite series. A finite series can always be evaluated. Because there's just a finite number of terms. Say there's only 12 terms, so you can plug them all in and figure out the sum. For example, a reminder of summation notation. We draw the sigma, we say the lower limit is 3, the upper limit is 7, and then we write our explicit formula, say it's -n squared. That means the sum would be all the terms from the third term to the seventh term of this sequence. So we would plug in 3 and get -9, plug in 4 and get -16, plug in 5 and get -25, plug in 6 and plug in 7, and then we can get an actual value for that sum. An infinite series, on the other hand, can sometimes be evaluated. So we saw with an arithmetic infinite series, that can never be evaluated. We're adding these numbers and the numbers keep getting bigger and bigger and bigger, or really huge negative numbers it could be as well. So an arithmetic infinite series cannot be evaluated. Because again, those numbers get really big, like 10 plus 20 plus 30 plus 40. Those are just going to get huge and into infinity. With a geometric, it can sometimes be evaluated. Take a second and just think about, how could this be? So if you think about the sequence 1, actually let's do 3 plus 12 plus 48 plus 192 and so on. That's a geometric sequence with a common ratio of 4. If you just look at those numbers are going to get huge as well, especially as n keeps getting bigger and bigger. So something like this, just like the arithmetic, it gets too big, it goes into infinity. We cannot evaluate that. But what we can evaluate is if we take the sequence 16 plus 4 plus 1 plus 1/4 plus 1/16 and so on. If we take that series, that actually can be evaluated. If you think about what the terms are going to start becoming, you're going to get 1/64 next, and the numbers are just going to get really, really small. You're getting these really small fractions that you're adding each time. So when you get to a certain point, you're hardly adding anything. You're just adding this really small fraction. So it turns out that you can evaluate something like that when the common ratio is a fraction between 0 and 1. So let's just start with the finite geometric series. and how we can come up with a formula for that. So take a finite geometric series, A1 times R, and so on. To find the sum of this, we know what the last term is going to be because it's finite. So we say the sum, S sub n, is the first term times 1 minus the common ratio raised to the nth power all over 1 minus r. So a couple reminders of what all these variables mean. S sub n just becomes the sum of n terms in the series. A sub 1 is the first one, the first term. R is your common ratio. And n is how many terms you want to add up. So the number of terms that are going to be a part of the sum. So that is the formula we use. So let's look at an example of how we can kind of use this in a finite geometric series. Again, finite means there's only a certain number of terms. Geometric means there has to be a common ratio from one term to the next. So if we look at this, 3 plus 6 plus 12 plus 24, we're going to keep adding until we get to the term 3072. So the first thing to notice, if we want to use this formula, S sub n is the first term times 1 minus the common ratio to the n all over 1 minus r. If we're going to start plugging into that formula, we need to know a couple things first. The first thing we need to know is A1. Well, that's given to us. It's 3. The second thing we need to know is the common ratio. If we look at this from one term to the next, we're just multiplying by 2. So the common ratio is 2. The tricky part to figure out in this case is what n is. Figuring out how many terms are in this series if the last thing I'm adding is the term 3072. So think about how we can figure out what term 3072 is. We might start with the explicit formula for a geometric sequence, which is a sub 1 equals a1 times the common ratio raised to the n minus 1. You should recall that formula from geometric sequences. Now we know when we plug in some n, we're going to output 3072. So we know a sub n has to turn out to be 3072. So we need to figure out which n will get us there. So plugging in, if we divide both sides by 3, we would get 1024 equals 2 to the n minus 1. This next part takes a little thinking. You have to think about 2 to the what power gives you 1024. So you could just keep trying different powers of 2. It turns out that 2 to the 10th is the same thing as 1024. So I'm just going to rewrite 1024 as 2 to the 10th. So if 2 to the 10th equals 2 to the n minus 1, that means 10 equals n minus 1. So n is 11. So we had to use that explicit formula to find out there are 11 terms in this series. The other way to do it would have just been to keep multiplying by 2 until we got to 3072, but then we would have had to write out all 11 terms. So now we know n is 11. Once we know those three things, we just plug into the formula. So the first term was 3, the common ratio was 2, n was 11, and the common ratio was 2, again gets plugged in here. So now we just have to take out our calculator and figure out what this huge sum is going to be. If you use your calculator, you can actually put that all in just one step of your calculator. So if we calculate that, we should get 6,141 by plugging that into our calculator. So let's see how we can do it given summation notation. Summation notation just looks a little different. Instead of writing out the sequence, it still gives us all the information we need to know. So let's set up our formula again. A1 times 1 minus r to the n all over 1 minus r. If you get in the habit of writing that down as your first step, the formula will really start to stick in your head. So the first thing we need to know A1, we need to know r, and we need to know how many terms we're adding. First thing we need to know is what the first term is. Now, you have to be careful here because this really means first term. Based on summation notation, it's telling us to start at n equals 0. So our first term is really when we plug in 0, not 1. Because remember, this lower limit tells us our starting point. So to figure out what the first term is, meaning plug in the lower limit, we would plug in 0 for n. When we plug in 0 for n, we have 1/2 to the 0. Anything to the 0 power is just 1. So that's 4 times 1. The first term we're adding in this sum is 4. The next thing is, what is the common ratio? Now, this looks similar to our explicit formula for a geometric sequence. So the important thing to remember is your r is just whatever is being raised to a power. So in this case, our r is 1/2. Even though it looks slightly different because this doesn't say n minus 1 like we're used to in our explicit formula, whatever is raised to that power exponent is your common ratio. In this sum, you're going to keep, to get one term, you're just going to keep multiplying by 1/2. Then we have to figure out how many terms there are. You're adding 0, the 0 term, the term when you plug in 1, the term when you plug in 2, etc., all the way until you plug in 20. That gives you a total of 21 terms. Remember, if this started at 1 to 20, that would be 20 terms, but you also have to include plugging in 0, so that gives you 21. Another way to do it, 20 minus 0 plus 1, 21. So now we know those three things, so we can plug in 4 as the first term, 1 minus r is 1/2, n is 21, so we have to do 1/2 to the 21, all over 1 minus 1/2. Again, using a lot of parentheses in your calculator, if you put this whole numerator in parentheses, divide it by this whole denominator in parentheses, you can do that all in one step with your calculator. When you do this, it turns out to be 7.999, so we're going to say that's approximately 8 as our sum. So take a minute in your calculator and make sure you can plug all of that in and get that 7.99 value. So like we said at the beginning, there's two types of infinite geometric series. So these are series that have no limit, have no end term. They go on forever. So in those examples we saw, sometimes those numbers are just going to get to be a really small fraction, and we can actually figure out what the sum is going to be. In the other case, we're not as lucky. The numbers are just going to get really big, like arithmetic, and we're not going to be able to figure it out. So the first type is when that common ratio r has an absolute value that's greater than or equal to 1. So for example, 3 plus 6 plus 12 plus 24 has a common ratio of 2. Those numbers are just going to get really big. So we say this type of sequence diverges. And what diverges means is the sum isn't going to approach some number because it's just getting so big. So we say there is no sum because the terms do not approach any specific value. There's no telling what these terms are going to get to. You just keep multiplying by 2. They're going to get huge. So there's no kind of way to narrow this down. Another example is, say your common ratio was -1. So something like that could be 5 times -1 times -1 times -1. In this case, the numbers are just alternating between 5 and -5, but they're still not approaching anything. If you just added one term, you would have 5. If you added 2 terms together, you would have 0. If you added 3 terms together, you would have 5. If you added 4 terms together, you would get 0. So those sums are not approaching any number. They're just alternating between 0 and 5. So that still doesn't help us. So the second type is when that absolute value of the common ratio is less than 1. So 1/2, 2/3, -5/8. All of those make the numbers get very small or get very close to 0. So we say that this type of sequence or series converges. It converges because the sum approaches a value as n gets very big. So there is a sum because the terms and the sum approach a specific value. They're approaching 0 because they're getting so small. So for example, if we had 1 plus 1/2 plus 1/4 plus 1/8 and so on, your common ratio is 1/2. These numbers are going to get very small, so we can actually figure out, even if we keep adding into infinity, what that sum is going to get very close to. Even if it's negative, so say 4 minus 1 plus 1/4 minus 1/8 and so on, your common ratio r is -1/4. Still, even though it's alternating, these numbers are getting very close to 0, so you can still figure out what the sum is going to be. So to find out the sum of an infinite geometric series, so these terms go on forever, we use a slightly different formula. We just say the big S sum of an infinite geometric series gets a little simple. It's just A1 over 1 minus R. So S is the sum of infinite terms. And A1 is still the first term that you're adding. And R is still the common ratio. So if you notice the difference between this formula and the formula for a finite geometric series, the only difference is you're taking out that n aspect because n no longer plays a part. So let's look at this first example. We first have to determine, does this converge or diverge? So to figure that out, we need to know the common ratio. The common ratio, the absolute value, is greater than 1 or less than 1. So it looks like we're multiplying by 1/2 each time. So that's our common ratio. If our common ratio is 1/2, that does mean it converges. If it converges, that means we can find the sum. So think about it this way. If we wanted to find the sum of just the first term, well, that's just 1. If we wanted to find the sum of the first 2 terms, that's 1 plus 1/2. That's 1.5. If we wanted to find the sum of the first 3 terms, that's 1 plus 1/2 plus 1/4. That's 1.75. If we added the first 4 terms, that's 1 plus 1/2 plus 1/4 plus 1/8. That gives us 1.875. And we could keep going on and on with this. If you look at these sums, the first sum is 1. 2 terms added is 1.5, 3 terms is 1.75, 4 terms is 1.875. You can see they're getting close to a number. They're not getting as big as quickly as they did in the beginning. So let's see what happens when we plug into that formula. Infinite series, because it goes on forever, it doesn't tell us where it ends. So it's just the first term over 1 minus the common ratio. First term is 1, common ratio is 1/2. 1 over 1/2, which is 2, means that's what our sum converges to. If I keep this pattern going on and on and on into infinity, it's going to get very close to 2. So that is actually what the infinite sum is for that series. We look at this second example. We're given summation notation this time. This indicates that it's an infinite series. So we're going to have to use the formula we just learned. Now looking at this formula, it is geometric because we have something raised to the nth power. So again, whatever is being raised to the exponent, that is your common ratio. So in this case, our common ratio is -5/4. Based on what we talked about before, the absolute value of this is slightly bigger than 1. So this is actually going to diverge. So that means the sum cannot be determined, or there is no sum. because it diverges, because that common ratio is bigger than 1. So those numbers aren't going to get close to 0, so there's no way to figure out what it's going to be. So last example, we're looking at this family saving for vacation. So it's in March, the vacation's in August. They know it's going to cost about $1,375. They're starting with $125, and each month they plan to deposit 20% more than the previous month, all the way from March to August. So we're going to figure out if they stay on that path, will they have enough money for the trip? Now notice the difference between this example and the ones we did with geometric sequences. This isn't asking how much money are they going to save in the month of August. It's asking in total, how much have they saved? So that's why you want to think series versus sequence, because you're adding all these months together, because what they save is the sum of all those months added together. So thinking about this, it's finite because you're only saving from March to August. So we're going to use the finite geometric series formula, which is a sub 1 times 1 minus r to the n all over 1 minus r. So a couple things we need to figure out. What's the first term? What's the common ratio? How many terms are we adding together? In the first month, in March, they start with $125. So that's our first term. They deposit 20% more than the previous month. So in April, they're going to deposit 20% more than 125. That means your common ratio is 1.2. Next, how many months are they doing this for? March, April, May, June, July, August. That's 6 months. Once we know these 3 key things, we can just plug into the formula. First term is 125. Common ratio is 1.2. There are 6 months, all over 1 minus that 1.2. Again, using your graphing calculator, using parentheses, you can plug that in all in one step into your calculator. And you should get 1,241 and 24 cents. So take a minute and make sure you can do that on your calculator. So make sure we look at what the question's asking. Do they have enough money? This is finally where this value comes into play. It looks like they're a little short. They needed $1,375. They only saved $1,241 and 24 cents. So they are still $133.76 short. So it looks like maybe if they had started 1 month earlier, they would have been able to save enough. So now I want you to pause the video and try the 5 checkpoint questions to make sure you can do these types of questions. And here are the answers. Number 1, the sum of 6 terms is 1,456. The sum of this geometric series with 4 terms comes out to be 65 over 27. Number 3, the common ratio was 2, so it diverges. There is no sum we can determine. For number 4, the sum of this infinite is 4.5 or 9/2. And number 5, you notice this converges. It is infinite. We can find the sum. The sum comes out to be 4.